Hi! Within this lecture, we're gonna start by learning about the differences between the classical computers and the quantum computers so that we can understand better how quantum computers work in upcoming lectures. And by classical computers, of course, I mean the regular computers that we use in our daily lives. So we need to understand how classical computers work in order to understand how quantum computers work in a different way. So maybe you know how classical computers work. Maybe you know about programming languages, maybe you know about bits. But we need to make sure that you know every detail so that you can understand the qubit term or quantum bit term in a detailed manner in the upcoming lectures. Okay, so maybe you have heard this concept. Classical computers only know about ones and zeros. So whatever we do, whatever we write, like in a programming language, or maybe we open an image file or a video file in our computers, the computer actually see that kind of information as only ones and zeros. So maybe you know this phenomenon, maybe you don't know. It doesn't matter, we're gonna learn about the details in this lecture and then we will move on to the detailed ones in the upcoming lectures. So why do classical computers know only about ones and zeros? It started with a very simple idea. We actually have some transistors in the processors that actually can detect whether we have a voltage, whether we have electricity or like electrons flowing through the current, like in a current through the transistor, so that we know whether there is an electricity or not. So if there is a voltage like 5 volt, then it's an up state or it's a 1. If we don't have it, then it's a 0. We don't have it. Okay, so it starts with a very simple idea. If we can have ones and zeros, if we can understand whether we have electricity or not in a transistor, then we can do everything. So what do I mean by that? For example, when we write some programming language, like when we write a Python code or Kotlin code or Java code, computer eventually understands it as ones and zeros in machine language. Okay, computer only sees ones and zeros, whether we write something in a much more complicated way, whether we write it in plain English. It doesn't matter for computer, it understands saying ones and zeros because that's all a computer can do. Okay, when we write something, and in Java, for example, it's called a high-level language. It's converted into assembly or in another intermediary language. Like we can understand a little bit, like a set of instructions, but eventually it's converted into ones and zeros. So if we look at some kind of an image that can show this phenomenon to us, you see ones and zeros in the upper side. So that's what our computer sees. And this add R2, R3, R4 thing is assembly, okay? And A equals to B plus C is actually Java code, high-level language code. So we can understand A equals B and B plus C, like 5 equals 3 plus 2, in an easy way. It's converted into assembly and then it's converted into ones and zeros eventually. Of course, we can even write programs or software with ones and zeros, but it would be very difficult for us to do that. You can imagine that, right? But since computer is just a machine, it's actually consists of a lot of transistors, a lot of processors. It can only understand whether there is an electricity in a given transistor or not. So they can it can actually detect only if something is 1 or 0, if there is an electricity or not. So the main idea, the genius idea, the revolutionary idea about this is that if we can store ones and zeros in a transistor or in any processor, then we can do everything. So what do I mean by everything? Right now, I'm actually recording my voice and you're seeing some stuff on the screen. This is all due to the fact that we can actually represent ones and zeros in a binary form. Okay, it's called binary ones and zeros. It's actually a number format. Consider a number 215. So it's again a number, but it's in decimal. So we know this stuff. But we can easily convert this into a binary. So how does it work? So maybe you have done this stuff. 5 multiplied by 10 to the power 0. Okay. And 1 multiplied by 10 to the power 1. And 2 multiplied by 10 to the power 2. So maybe you have done this experiment or this exercise in high school or even in elementary school, right? It's very easy for you to do. So if you add up all these things over here, it gives you 215. So why does it matter? Because we are in the decimal system, right? So it goes for the same as 514. So 4 multiplied by 10 to the power 0, 1 multiplied by 10 to the power 1, and 5 multiplied by 10 to the power 2. If you multiply all of this, if you sum all of these terms, you get 514. So we can do this for binary numbers as well. Consider this number 11011101. So can we convert this number into binary, from binary into decimal form? Of course we can. So right now I have 1 over here and I should multiply it by the power of 2's, right? 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. Rather than using 10, I'm using 2 as a base because in binary I only have 2 numbers, 1 and 0. In decimal I have 10 numbers, right? It's coming from 0 to all the way to the 9. So if you multiply everything with the powers, if you sum it all together, then it means 109. So 1101101 in binary equals to 109 in decimal. So it's very cool, right? We can convert binary into decimal. We can convert binary into any number that we know in the daily life, and we can do vice versa. So right now we know that we can represent numbers. We can represent daily life numbers in binary form so that we can actually represent them in electricity as well. So consider this. So this is hexadecimal. In hexadecimal, it's another number format, and we have, as you can see, we have like 16 numbers over here, starting with 0, ending in 15. And they assign some letters to represent 10, 11, 12, 13, 14, and 15. And you can see something like this in a computer reverse engineering operation, for example, A for F6. So if you follow the exact same pattern that we have seen before, you can just convert this into binary or decimal. So let's see, A equals to 10. And we multiply it with the power of 16 because we are in a 16 number system right now. So 16 to the power 1, 16 to the power 0. If you add up all of those things together, you have this number, 42,230. So A for F6 equals to 42,230 in decimal. Of course, you can convert this into binary form as well. So we know that we can represent numbers whether they are too big or too small in binary. And we can do the same thing not only for numbers. For example, we can do the same thing for letters as well. We can actually assign some letters to some binary numbers and just know that A equals to 65, for example, or B equals to 66, C equals to 67, so that I can tell my computer, if you see 65 in a letter context, in a alphabetical context, then don't convert this into binary or decimal. Just convert this into an ASCII form to A, for example. So I can assign each letter to different binary representation so that I can represent everything in an alphabetical order or in any order that I want. So this table is coming from ASCII representation, and as you can see, they assigned some numbers to some letters, and of course we have a lot of different representations rather than only ASCII right now, because there are a lot of different alphabets on world. So you see that some kind of special characters or special operations over here, like null or anything else, or special characters like decimals or hashtags over here or dollar signs. But it really doesn't matter as long as we assign something like emojis to some kind of decimal number or binary number. Then our computer will know what it is that it's dealing with, right? So we can represent the letters in a given way. So that's cool. Now I know that I can represent letters in the form of electricity. If it's a 5 voltage, then it's 1. If it's maybe no voltage at all, it's a 0. And I can combine these ones and zeros all together to create the letter A or B or C or an emoji, for example. So this is very powerful and this is very revolutionary, as you can see. But of course, this is not only yet. So how can I create an image? How can I create a video? How can I create a sound? I can use the same logic. Okay, the thing over here, the differentiating thing, is the context. As long as I can say my computer, this is in the context of an image, I can easily represent an image, right? So scientists came up with this idea that they can actually create any color with a coding system like RGB or red, green, blue. If we combine red, green, blue in a way that is starting from 0 all the way to the 255, we can have all the colors in a palette, in a given palette. And of course we can convert this RGB into binary form as well, so that I can represent any color with the binary representation as well. So if I can create any color, then I can multiply or combine all these pixels. So pixel is the smallest part that you can see on the screen. Okay, so I can say to my computer that left hand side is going to be green, right hand side going to be blue, and so on and so on, and it will create that image for me on my screen. So I can easily just create images. And what are the videos, by the way? Videos are sequential images, right? So you see images one by one in a video, so you can easily create a video using ones and zeros only. So idea started with that. We can store ones and zeros in a transistor. So what do I do with that? You can do anything with that. For example, if you come over here and if you look at this example, you will see that we have zeros and ones, right? So I have 1, 2, 3, 4, 5, 6, 7, 8 zeros. So I can represent 8 zeros, or I can represent 8 ones over here. So if you just have the 2 to the power 8, it will be equal to 256. So if I want, I can represent all the numbers starting from 0 to the 256 with binary in a classical computer in only one shot, right? If I have only 8 bits, by the way, 8 bits equal to 1 byte, so I can represent every number between 0 and 256 in one shot. So I can represent 255, 254, or 1 or 10 or 14, I don't know. But in quantum computers, due to the fact that we can have some quantum properties like entanglement and superposition, we will see what are those, by the way, don't worry. We can represent all the numbers starting from 0 to the 256 at the same time, simultaneously. So as you might imagine, it's a great possibility, or it's a great potential that we can use over there, right? So rather than only one number between 0 and 256, we can represent all the numbers simultaneously. And it's again a revolutionary idea. And it's almost as big as finding a regular or classical computer for the first time, right? Because it increases the possibility or the calculation possibility in an enormous way for only some kind of specific purposes, and we're going to talk about those. So quantum computers can change our lives in a substantial way if we can leverage this potential. And we're going to see what are the obstacles around throughout the way, and where are we right now, and also what we can do to make it better, and how we can understand it in a perfect way so that we can be actually increasing the knowledge of quantum computing for ourselves and for the society as well. Now, this is how classical computers work. We're going to stop here and continue with the next one.